Yeah, hello everyone. So I will discuss here some parts or some aspects of the fluid mechanics, and first of all, I will discuss the kinetic part of it. So this kinetic part will include the study of fluid motion without the forces. So forces and stresses will not come here, and we will study the motion of the fluid. This is called the motion of study of motion of fluid. So. um So there are two types of descriptions available for the fluid motion. The first is Lagrangian approach, and the second one is Eulerian approach. So in Lagrangian part, this is also called a particle based approach. So in that, uh, whatever parameters we have to study is for a single particle which is traveling, uh, which has the trajectory. Let's say this is the trajectory, this is the velocity, uh, and this is the path of the particle. And we will study, will focus on that single particle only. That is called the Lagrangian approach. And for the Eulerian approach, it is a uh, fixed region based. So in that uh, Eulerian approach, we will fix a region uh, inside the fluid. Inside the fluid, we will fix a region. We will fix a region, and we will study the fluid which is inside that region only, not outside. So we will study all the parameters like the velocity, the momentum, the flux, or so here also the velocity, the direction. So that is in the Lagrangian approach, and this is Eulerian approach. So now let's say we have a flow property, we have a field flow property or flow field property uh, f, which is a function of r. R is the distance, and R is also a function of t. Given that uh, the initial coordinates means at t is equal to 0, R is equal to R naught. That is given already, and the f is function of R and t also. And let's say this is our coordinate system, and this is a particle going, a particle here started at R naught, at t naught, and this is, let's say, uh, R at t. So this is the particle path. Okay, so this is the Lagrangian approach. Lagrangian approach we are dealing with. So uh, in that approach, we will just take the uh, differentiation of that property with respect to the time. So we will define d by dt of f, which is a function of r, and which is also a function, r is also a function of t, given that r naught at t naught and here t. So that we can write it as the partial f partial t plus partial f by partial r1, then dr1 by dt plus partial f by partial r2 dr2 by dt plus partial f partial r3 dr3 by dt. So we can write it as df by dt as d del f by del t. Now we can write del f by del r1. Now we can write dr1 by dt. Uh, so r1 is just the position vector, right? So when we differentiate the position vector with respect to time, we will get the velocity of uh, that at that point. So we'll write u1. So and del f by del r2 u2 plus del f by del r3 u3. So here u1 is equal to dr1 by dt, u2 is equal to dr2 by dt, and u3 is equal to dr3 by dt. Okay, so we can also write df by dt is equal to del f by del t plus in the vector notation I will write u dot del f is equal to, or we can also write it as a total derivative of the property with respect to time. So so it will become df by dt is equivalent to del f by del t dot plus u dot del. So this is the total derivative we get. So in that also, if you see, so you can see here. So there is a flow field property f, and del f by del t is the temporal part of it. So this is the temporal part of it, and this is the advective part in which uh, this is advective. So this is u dot del f. So now some of the terms are here. I will discuss some of the terms here. First of all, there is the steady term, steady or unsteady fluid motion. So for steady fluid motion, the property will not change with respect to time. So in that case, del f by del t will is equal to 0. And for unsteady term, for unsteady case, del f by del t uh, is not equal to 0, means f will change with respect to time. So there is a change, so that's why it's not equal to 0. And uh, and the second thing is for the advective part. For the advective part, we can say if u is equal to 0, then advection is 0, and if also del of f, means the gradient of f, the flow property, is 0, then advection also becomes 0. And also if the velocity and the gradient of the flow field are perpendicular, so that's why they will the dot product of them will be 0 because they are perpendicular. So if u perpendicular to uh, del f, so then also the product will be 0, and in that case also the advection part will be 0. Okay. So now this is all I expressed in the vector form. So now if I have to write in the tensor form, so in the tensor notation, it will be d capital D f by dt is equal to del f by del t plus ui del f by del xi. So that is in the tensor notation.